All right, Newton's third law of motion. Newton's third law of motion is the one that people can readily recite, but not really explain what it means, what it is, and how it deals with motion. So in some respects, it's the best known law, but it's the least understood. It states, for every action, there's an equal but opposite reaction. What the action and reaction refer to in this law are a pair of forces that interact with each other. One of those forces would be called an action force. The other one would be called a reaction force. So we could say for every action force, there's an equal but opposite reaction force. So understanding this law is really about understanding these two forces, what produces them, what they act upon, and how these forces relate to motion. Let's start with what the action force is. An action force is the force that initiates the interaction between two objects. The example I'll use is pushing on a desk. If I push on a desk, my push, what I do, initiates that interaction between the desk and me. My push would be the action force. Now, when I push on the desk is going to respond to what I do. I'm going to push on the desk. I'm going to apply a force to it. And at the same time, the desk is going to apply a force back on me. What causes that reaction is just simple electrical repulsion. You think back to chemistry, the outside part of an atom is the electron cloud. And the electron cloud has a negative charge. So the outside of my atoms are negatively charged. The outside of the desk's atoms are negatively charged. When two negatives get together, they repel each other. So if I push on the desk with 100 newtons of force, it's going to repel me with 100 newtons of force. That return force would be the reaction force. So again, an action force is what starts the interaction between the two objects. The reaction force is how that other object responds. So if I push on a desk, my push is the action force. The desk will push back on me. That's the reaction force. So for every action force, there's an equal but opposite reaction force. That's the law. It applies to every time a force is exerted. If I push on the wall will push back on me. When I push down on the floor pushes back up on me. When I grab a doorknob and pull it, the doorknob pulls back on me. When I go to lift up a pencil, I apply the force to the pencil applies the force to me. Every time a force is applied, it always happens in pairs. It is an action-reaction pair. The force that initiates the interaction is the action force. The way the object responds is the reaction. They are equal in size. So if I push on the desk with a 100 Newton force, the desk pushes back on me with a 100 Newton force. These forces are equal in size, but opposite in direction. Now, you've heard that before. That came up in one of the videos, the one that dealt with balanced and unbalanced forces. Here's the deal. Here's the tricky part. These forces don't cancel. And the reason why these forces don't cancel is because they act on different objects. Back when we were learning about balanced and unbalanced forces, we talked about gravity and normal forces. If I take an object and sit it on a surface, gravity is going to pull down on it with a force equal to its weight. So if that object has a weight of 5 newtons, gravity is pulling down on it with a force of 5 newtons. And we know the surface it's sitting on is going to push upwards with an equal force. So if I take the eraser from my smartboard and stick it on my hand, gravity is pulling down on the eraser with a force equal to its weight. so maybe a half a Newton. My hand is pushing up with an equal force, half a Newton, in the opposite direction. Those forces cancel. And the reason why those forces cancel is because they both act on the eraser. Gravity pulls down on the eraser. My hand pushes up on the eraser. Acting on the same object, those forces will cancel. Action-reaction forces act on different objects. When I apply my force to the desk, it's the desk that's being affected by my action force. When the desk pushed back on me, it's me that is being acted upon by that reaction force. The forces are equal in size. The forces are opposite in direction. The forces are acting on two different objects. And as a result, they do not cancel out. And that's one of the hardest things for students to wrap their head around. You learned about equal and opposite forces with balanced forces, and you learned that they canceled out. Now I'm talking about equal and opposite forces again, but this time they don't. You got to understand that these forces are acting on different objects, and because they're acting on different objects, they do not cancel. Take a look at another example, and we'll use a free body diagram to kind of wrap our heads around this a little bit. It's a classic example. It's used in a lot of physics classes. Someone kicking a football. When this kid comes along to kick the football, he's going to apply a force to the football. That's the action force. The kicker starts the interaction. The football is then going to push back on the kicker. That's the reaction force. What we're going to do is we're going to do the free body diagram for the football. And we're going to focus only on the forces that affect the football. So let's think about what's going on here. Gravity is going to pull down on the football. Everywhere on Earth, you're going to have gravity. And everywhere on the Earth, you're going to have something that counteracts gravity. So gravity is going to pull down on the football. What's going to counteract the gravity in this case is normal force. The football is sitting on the ground, so the ground is going to push up on the football. So when we draw our free body diagram, we're going to have gravity pulling down. We'll have the ground pushing up. My kicker is going to apply a force in this direction to kick the football. So the way I draw my free body diagram, I'm going to draw the applied force over to the left. And to the right, we're going to have a force, but the right force is not going to be the reaction force. The force to the right is going to be the little bit of friction between the tip of that football and the ground. So it ends up looking like this. There's my gravity pulling down on the football. There's the normal force of the ground pushing up. Those are balanced forces. They're equal in size, they are opposite in direction, and they are both acting on the football. So those two would cancel out. FA is my applied force. This is the kicker hitting the football, that direction. And what's resisting that is that little bit of friction between the football and the ground. The reaction force is not on here. And the reason why the reaction force is not on here is because the reaction force doesn't act on the football. When you draw a free body diagram, you only draw the forces that act on that object. The reaction force will act on the kicker's foot. So if we were going to be drawing a free body diagram for the kicker's foot, that's where you'd find the reaction force, two different objects. And that is, again, why those forces don't cancel out. So let's apply this to some situations because that's what the standard says you have to be able to do. Let's think about what makes a rocket fly. You ever seen a rocket launch on video? You see all kinds of fire coming out of the engine of the rocket, huge plumes of smoke on the ground, and the rocket rises out of those plumes of smoke. And that leads to the biggest misconception. Many adults believe that for a rocket to take off, the flames, the exhaust, have to push off against the ground. And that's just not true. Because if that were true, there would have to be a trail of fire all the way from the ground, all the way up into space. If a rocket engine truly had to push off the ground, you would have to have a column of fire from the ground to outer space, and that's not what happens. What makes a rocket fly is a simple action-reaction pair. The engine is pushing the exhaust, those flames, downward. That's the action force. That's what starts it. And then that exhaust, those flames will push back up on the rocket. And it's that upward push from that exhaust that makes the rocket fly. Here it is in a visual representation. You've got that fire that shoots out of the back of the rocket. And basically what this rocket engine is doing is just throwing those flames downward. Throwing them downward. Because they are pushing the flames downward, the flames are going to push back up on the rocket. That reaction force is what makes the rocket go. Again, the action and reaction force will be acting on different objects. The engine of the rocket pushes downward on the flames. The exhaust pushes upward on the rocket. So again, the action-reaction pair is exerted on two different objects, and because of that, they don't cancel out. Consider swimming. Think about swimming and which direction you push on the water. When you swim, what direction do you push on the water? If you said backwards, you're correct. When you swim, you push backwards. That's the action force. What's the reaction force going to be? If you push backwards on the water, the reaction force will be the water pushing forward on you. Again, two different objects. Your action force pushes backwards on the water. You push on the water. The water pushes forward on you. Again, it's an interaction between two objects. You push backwards on the water. Water pushes forward on you. They're equal in size, they're opposite in direction, but they don't cancel out because they're on two different objects. You could stand here and do this all day. You'll look stupid. You won't go anywhere. The reason you won't go anywhere isn't because there's no action-reaction forces there. When you push backwards on the air will push forward on you. There's an action-reaction pair there. But you don't go anywhere. And it's not that those forces are canceling out, not at all, because again, they act on different objects. You push back on the air pushes forward on you. The reason you don't go forward is because there's another force involved here. When the air pushes forward on you, there's another force that opposes its motion, and that's the friction between your feet and the ground. And the forward push of the air is not enough to overcome the friction between your feet and the ground. So you don't move. In the water, the forward push of the water is stronger than the forward push of the air and enough to overcome your drag as you move through the water. Let's consider a car moving to the right. So you're standing here, you're looking at a car that's going that way. I want you to think about the tires on the car. Which direction do those tires turn? Do those tires turn clockwise or counterclockwise? Again, you're standing here, car's in front of you, car's going that way. Do the tires turn clockwise or do they turn counterclockwise as the car goes that direction? Said clockwise, you're right. Now I want to think about the interaction between the tire and the ground. When the tire hits the ground, which direction is it pushing? Again, you're standing here looking at the car, car's going that way, tires are turning clockwise. When the tire makes contact with the ground, which direction is the tire pushing? If you said to the left, you're correct. And the tire is rotating in this direction. When it hits the ground, it's pushing to the left. So if the tire is pushing on the ground to the left, which direction is the ground pushing? If you said to the right, you are correct. The action force is the tire pushing the ground to the left. The reaction force is the ground pushing the car to the right. And it is that return force of the car that makes the car go. Tires push to the left, action force, road pushes to the right, reaction force. And it is that reaction force that makes the car move. Which begs this question, why is it hard to drive on ice? If you're thinking you can't produce your action-reaction forces, you're right. Tire turns and pushes to the left, but the road can't push back to the right, so the car doesn't go anywhere. Same thing would happen when you walk. Said it in the last video, I'll say it again. The best drivers are the drivers that understand physics. When you understand the laws of physics, when you understand the equations of physics, it makes you more capable of predicting what your car is going to do. With the momentum, you learn and you get a feel for how much you have to slow down and reduce your momentum to get your car to do what you want it to do, to turn, to stop, etc. You get a feeling for how you're going to have to treat your car when there's ice on the road, when there's water on the road, etc. You get a better understanding of what your car is going to do, how your car is going to behave when you understand physics. It's really important, I think. I mean, the way I drive as someone who teaches physics is quite different from the way that most people drive. Almost everybody drives. For example, I don't speed. And the reason why I don't speed is because I'm not afraid of cops, etc., etc. I understand that it's pointless. I understand that you gain nothing when you speed. Speed is distance over time. I know that. And I know if I'm driving 55 miles an hour on a 20-mile trip, I can solve that for T and figure out how long it's going to take me to get there. If I do that math real quick, it's 20 divided by 55. That's 0.36 hours times 60. That's 21.8 minutes. Call it 22 minutes. I know if I drive 65 on that same 20-mile trip, that it's going to take me 0.307 hours. I know that that is 18 minutes. So at the most, I know that my 10 miles an hour speeding is only going to get me there 4 minutes faster. Beyond that, I know that that's an ideal situation. I know that that's in a perfect world. We don't live in a perfect world. We've got stoplights. And I know that what happens most of the time is the person who's driving 65 gets to the stoplight before me, which means they spend more time stopped, which means that lowers their average. So they may be driving 10 miles an hour over the speed limit, but their actual average is only 2 or 3 miles an hour faster than mine. See what I'm saying? And if they're only going 2 or 3 miles an hour faster than my average, the reality of it is really something more like this, where they're maybe only averaging 3 miles an hour more than I am. And they're really taking 21 minutes to get there. So in reality, their 10 miles an hour of speeding is really only getting them there a minute quicker. And to me, that's not worth an $80 speeding ticket and doubling my insurance rates. It just doesn't make sense. I understand these things. I know these things. This is true. It's research proven. In fact, the research says it's only 15 seconds. The average speeder only gets to their destination 15 seconds faster than someone who drives a speed limit. So I don't speed because it doesn't make sense. It doesn't accomplish anything. It just uses more gas and runs me the risk of getting tickets. Don't need that. I pay $45 a month to insure my 3-year-old Jeep. Don't you wish you paid that little? And if you want to pay that little, you make sure you have a clean driving record. That's the only way to do it. Back to this, action-reaction forces are responsible for all motion. That's why it is a law of motion. And as we've seen through all the examples I've done, for an object to move, it has to push off of another object. For me to walk, I have to push off on the ground. And if you think about the way you walk, you push backwards to make your body go forward. I have to have that push off from the ground to make my body work, to make my body go. For any motion to happen, one object has to push off another. And if you didn't have those action-reaction forces, you wouldn't have that. There'd be no motion. There'd be no way to get moving. Think about walking on ice. It's hard to walk on ice because you can't get the pushback. You can't push off on the ground like you normally would. The other reason we say it's responsible for all motion is you could not apply a force without action-reaction forces. My initial example was pushing on a desk. I push on the desk pushes back on me. It's that reaction force, that push back on me, that keeps my hands from going through the desk. If the desk couldn't push back, I'd be like a ghost and I'd push right through it. Nothing would happen. So action-reaction forces are responsible for all motion. When something wants to move, it's got to push off on something else. When you want to apply a force, you need the reaction force or you can't do it. That's why this is one of the laws of motion and perhaps maybe the most important one. Like I said, the most easily stated, but least understood.